this light's going to go on and that's going to light up.
Anticipation.
There we go. Triggering.
I pushed the button. So what is that sound that we just heard?
That's the sound of a $150 million plasma collider, blasting jets of super hot ionized gas at hundreds of miles per second.
We're at TAE Technologies, a 20-year-old startup that hopes to finally achieve nuclear fusion. It's the same energy that fuels the stars, but harnessing it here on Earth has been a scientific dream for decades.
Fusion power plants would mean plenty of energy, no carbon emissions, little long-term radioactive mess, and zero chance of a Fukushima-like meltdown. Governments, universities, and private companies have been pursuing fusion since the 1940s, and we're still nowhere near adding a fusion power plant to the grid. But in February 2018, a panel of experts published a list of game changers for fusion research. And at the top of their list were advanced algorithms like artificial intelligence and machine learning. One of the private companies chasing fusion is TAE, which began collaborating with Google a few years ago. Together, they developed machine learning tools that TAE thinks could finally bring fusion within reach. So we headed to a nondescript stretch of Foothill Ranch, California. We wanted to see just how far along TAE Technologies is, and where, if anywhere, AI enters the picture.
So right now, we're looking out towards the main vessel, the experiment. See all the blue cabinets around? They are our power supplies, primarily for the magnets which help to control and shape the plasma that we are heating.
Our guide is Eric Trask, a lead scientist at TAE Technologies. He's taking us on a tour of Norman, the company's plasma collider. Inside, magnetic fields propel and control the super hot, spinning clouds of ionized gas called plasma, while particle beams heat it to temperatures hotter than the sun's core.
The goal of this machine is to show that we can heat up our plasma to high enough temperatures to show that it is relevant to make a fusion power plant out of.
All attempts at fusion involve smacking lightweight particles into one another at temperatures hot enough for the particles to fuse. That produces a new element plus energy. In the stars, fusion occurs when hydrogen nuclei fuse to form helium. There are a few different ways to try and replicate this process on Earth. Some experiments control the plasma with magnetic fields inside a massive metal donut called a tokamak. TAE twirls the plasma inside a linear machine named Norman. Sounds great, but none of this has produced enough energy to be useful for a power plant. A machine in the UK called JET did set the world record by generating 16 megawatts of fusion power, but it took 24 megawatts to heat up the plasma, and even more electricity to contain it. So the whole thing was a net loss of energy. TAE's Norman machine produces some fusion reactions, but not many, according to the CEO, Michael Binderbauer.
So things get hot enough that, yes, occasionally a few elements actually collide hard enough and you get fusion. And we actually use this for diagnostics purposes. Now, this isn't bulk fusion yet, right? So this wouldn't be economic. This makes a handful of events. But as we go up the scale, eventually we'll get there.
That's a goal for the future. A fusion reactor that runs for months at a go. For now, the goal is to produce a plasma that's 30 million degrees Celsius for 30 milliseconds. To get there, the team fires Norman 50 times in a day for just milliseconds at a time. Each shot, they may tweak thousands of variables like the timing, the shape of the magnetic field, the voltage of different power supplies, or the amount of plasma. Since the machine came online, it's fired over 11,000 shots, each one a bit of a blind stab at the optimal variables.
And we have a fault on M1N. Do we know what happened there? Stopping the shot.
So what happened?
So there's potentially a resistor that's gone bad, or a board that is reaching an overvoltage and is tripping something inadvertently.
It's impossible for a person to keep all those variables in their head, or to change them one at a time. That's why the team is collaborating with Google, using a system called the optometrist algorithm.
The advantage of one variable at a time is you know exactly what happened and why, which makes prediction and model building very easy. You can do that as long as the number of variables you have is not very large. How do you do that in 4 dimensions? Or 20 dimensions?
The algorithm is what lets them change scores of variables in each shot. If the team thinks the new combination produced better results than the last one, they pick one path of pre-programmed shots. If it's worse, they pick another. Hence the name optometrist. Is shot 1 or shot 2 closer to viable fusion? 3 or 4? 654 or 655? According to Eric, what's happening here is really machine learning rather than AI. Right now, it's still the humans making the call about what's better and what's worse.
We've gone through countless classes in undergrad and graduate school, time in the lab. So our knowledge is being used to produce data. Now, at some point, an AI system could be used, could be trained on the knowledge we're gathering. We're not quite at that stage yet.
We asked some other fusion researchers what they thought of TAE's approach. Julian Cates-Harbeck, who worked with Princeton's Plasma Physics Laboratory, and Christina Rea at MIT. They use machine learning a little differently, but they're intrigued by TAE and the optometrist.
This algorithm supports human decision making, but doesn't take away the human out of the loop. So it's sort of this beautiful synergy between the human and the machine.
Julian and Christina have each developed algorithms to predict when the plasma might misbehave in order to keep it under control. The methods differ, but Christina says fusion experiments are just so data-heavy that it's natural for machine learning to help here and there, within reason.
There are many low-hanging fruits in our field that can really benefit from using this advanced statistics that lies under the hood of AI in general. Of course, we are not getting to the point where we are, building a self-driving tokamak.
These teams all see machine learning and AI the same way, as important tools, just not as a panacea to all of fusion's problems. Right now, there's no such thing. The TAE team is still thinking in milliseconds and looking for one good day at a time.
If we can get there in one day, great. It probably will take more than one day.
Is that a good result, the plasma at 20 million degrees for 10 milliseconds?
That would be terrific, yeah. Champagne would be flowing by now.
Hey everyone, this video is actually part of the Real World AI, a special issue here at The Verge. This week we're bringing you all sorts of stories about how AI is being used in the world today. So if you want more, go to The Verge's YouTube channel or go to theverge.com/AI.